Good morning, good afternoon, good evening, depending on when you're watching this. My name is Dave Larson. I'm the Senior Energy Engineer at Brown University, speaking to you right now from Providence, Rhode Island. And the project we're going to talk about, I was actually the project manager before in a previous role. I've been here about 10 years. Frederick?
Hello, everyone. So Frederick Marchand, Director of Technical Solution at Ecosystem Energy Services. So welcome to this presentation.
So why are we here? Well, we're going to talk to you a little bit about a project that came up at Brown. And the reason that we had this project, we had some ambitious greenhouse gas reduction goals. And we were getting pretty close to the deadline. We were about 4 or 5 years out. We could see the writing on the wall. We weren't going to make it. We had plenty of funding available, but the problem is we had this 8.5% IRR funding requirement. So we had to meet certain payback criteria. And we had a lot of electric projects that were getting approved and everything. That was great. The problem is gas was too cheap. And we really needed gas savings to meet our goals. Their 42% reduction is what we were shooting for. And the other problem is we have this sort of vintage campus system that we were working with, okay? Actually, many vintages when you look at it. Very well maintained, but we had steam boilers at the central heat plant. You can see we had three 80,000-pound steam boilers feeding a high temperature hot water system. But then we also fed out into some hubs that would make steam from that high temperature hot water and use it as a sort of intermediate distribution system. And some of those hubs were pretty old, like 50, 60 years old. And so we had a lot of legacy systems around. So we were having trouble trying to find these gas savings given what we had in front of us, the IRR requirement and the physical plant. So we wanted to achieve that goal, but we also wanted to simplify our maintenance and improve our reliability. So that's when we called Ecosystem in to try and help us find a solution to all of these problems.
So this is when we came in. The rules of the game was clear. We had to save something around like 10,000 tons of GHG per year using 8.5 R as our leverage for this project. So soon it appeared that we had to investigate the whole distribution process for heating in the entire campus. So as David already mentioned, most of the building level energy saving was pretty taken care of. So we had to take closer attention to production and distribution so we can find losses on campus and make sure we can address that correctly.
And as I mentioned at the start, we have a bunch of different legacy systems on campus, and this kind of shows how complicated some of the process of getting heat from the gas main out to the final end user was. We had a mixture of old and really old systems when you get right down to it, but they, as I said, they were well maintained. What happened over time is as we built new systems, we would often use existing systems to we would leverage them. So we had a lot of existing steam distribution systems out in the hubs and in the buildings that we continue to use, even though we might have, hot water terminal devices. Those intermediate steam systems really made things more complicated and expensive to maintain. And we'll talk a little bit more about that during the presentation, but also made things less efficient.
Steam distribution system. Back in the days, many steam distribution on campus were surveying the original building on campus. Then the location of the central heat plant was changed, and they had to come up with a new way of distributing heat on campus. So they've built this heat plant, and we'll see later exactly where on the map, but they had to produce high pressure steam because they were using at the time a cogen to produce electricity for the entire campus. So as David mentioned, they had many systems built over old system just to serve the existing need for building and process on campus. But now, as the campus was heated, there was no cogen, but still there was need for process steam and building steam heating system. Though those systems are not the most efficient, so if we want to improve distribution efficiency, we had to get rid of these steps in the loop. So basically, our goal was to go from this old system to this new system where we don't have steam as a intermediate step from the plant to every building. But again, we had to make it happen with an 8.5 RRR. So this is the distribution high temperature loop for Brown University's campus. For those who don't know what is high temperature hot water, is basically water at 350 degrees Fahrenheit that is kept under pressure and distributed underground all over building, so you can produce either hot water but also high pressure steam. So it's a very complex system. So we had many challenges to tackle if we wanted to increase our campus efficiency by getting rid of steam. So first, we have the central heat plant. We've got like high pressure steam boiler with heat exchanger, direct contact heat exchanger to produce that hot water under pressure. Then we've got process load on campus. So we don't want to change like $1 for 4 quarters. So just by changing steam technology to gas technology. So those has to be addressed in a smart way, and we're going to talk about later. And the next part is all of the steam distribution hub on campus. So they had 6 steam distribution hub that had to be converted to the hot water if we wanted to increase our loop efficiency. So we came up with this plan for Brown University. We said, okay, first, let's address the process load, because we want to lower the supply temperature. That was one of the stops we have if we want to increase efficiency, because lowering like loop temperature will reduce all the losses through all the entire underground system. But this, if we want to lower the temperature, it creates other problem. It creates distribution problem. You're increasing the flow on your entire high temperature system. So we had to come with solution to not increase too much the flow on certain section of the loop. So we have to have an hydraulic model that represent the reality of the distribution system and leave some spaces for campus addition in the future. Also, the third phase will have to convert the existing steam plant to hot water. We don't want to maintain this complex operation where you got a temperature that it's related to the system pressure. So we want to like lower the supply and return temperature of the loop. So we have to address this way of producing hot water at the plant. The fourth step will be to reuse existing piping for hub conversion, because we don't have time and money to do all those things. We have to come with like good way, and a good way could be to repurpose all the existing piping for all steam distribution piping to be converted to hot water, and that will probably serve better the goal of our project. And obviously, reducing building demand will have a direct impact on our efficiency, and also reducing the emission goal.
Ecosystem presented this plan to us, and it checked off all the boxes. It achieved the savings we were looking for. It did make things less complex overall for the campus, and we saw a lot of benefits to it. But this is pretty much the expression on my face when I started getting into some of the details. So no, there were some risks that we saw. We had many concerns. Because normally we do a big project like this, everything's new. You get new boilers, you get new pipes, you get new air handlers. And this was a very, very innovative way to get a lot of new, but also reuse a lot of existing. So, but we did have some concerns. You know, we're talking about reusing steam and condensate piping, some of which has been out of service for 40 years. We're talking about converting 3 80,000-pound steam boilers that are like 50-something years old. to forced hot water, that made me nervous too. And we're also talking about swapping out coils on existing air handlers, that some of which feed vivariums. You know, you can't really shut those down for a couple weeks. I mean, the benefits of the project look super, but we recognize that our crew has to maintain this over time. So we started to look at what are the risks, and if there are risks, what can we do to mitigate them, and then get the benefits of the project. So we had to examine the perceived risks and the potential benefits, so our engineering and operations folks would, at the end of the day, feel comfortable and not look like Dave's little diagram here. So, go ahead. Next slide.
And for sure, the first step was to go over engineering and operation. We had to make sure everyone understand the misconception about replacing piping will eliminate risk. So replacing piping does not necessarily mean that you're going to eliminate risk. You're going to reduce risk, but this will come as a cost. So we were starting changing the way we were expressing it by reusing piping is a saving opportunity, but we had to come with good way of doing it and explaining why we would use it so people can understand, but also understand that we would control the risk associated with reusing all of this piping.
Right. So, you know, Brown did recognize that converting all these steam distribution systems over to hot water made the system simpler, which was one of those boxes we needed checked. It was great. Instead of having to operate and maintain steam converters, condensate systems, traps, receivers, pumps, in a lot of cases, all that went away and we were left with an injection valve, okay, which is much simpler. So, you know, there were also some benefits that we saw with reusing some of this equipment. The cost obviously went down, material and labor up front. Less disruption. This was a huge thing, and we'll talk about this a little bit more when we talk about details on one hub in particular. But you know, when you don't have to install a bunch of new pipe, there's a lot less disruption, and then quicker implementation as well. On the risk side, and Frederick's already kind of mentioned part of it. We'll get into details. You know, we set up several systems and protocols to reduce the real and even the perceived risks. Some examples are listed here. You know, more time and money in the engineering side of things, testing protocols to examine existing equipment that we're reusing. We'll talk about a contingency funding that we had, and then pre-functional testing, commissioning, all those kind of things that really make people more comfortable at the end of the project that things have been installed and they're operating correctly.
So as Dave mentioned, like he mentioned, like putting more money into engineering. What it means, like we say that it's investing in engineering. Yes, there's a part of it that would be invested in more survey for steam pipe, just to understand better and make sure we are reusing the right piping. We're not like reusing rusty pipe or pipe that are already leaking. So yes, there is a part of this money in investing in engineering that is used for more surveying. But most importantly, it means that we have also to find ideas out of the box. We have to find leverage because, again, if we want to go forward with this project, we have to find the leverage, the savings that will justify investing all that money in all those investigations on the existing network. So some of the idea on the screen right now are example of what we've proposed to Brown. So the example on the left, as David mentioned, we had to convert many of the ventilation system, air handling unit, sometimes like 100% fresh air in an air handling unit. We had to replace the coil already to convert from steam to hot water. But while doing this disruption, there's also an opportunity for us to go and perform a heat recovery system, because if you got 100% fresh air system, you've got the exhaust as well. So most of those systems, when you're trying to retrofit a new coil, you're always stuck with I don't have enough space to install my heat recovery coil. So what we've proposed, we came up with this innovative solution, and we've combined the heat recovery glycol portion of the coil with the heating section of the coil, connected to both the exhaust and our heating system. So that way we could have installed the coil in the same space that that Brown already used the steam coil, without creating too much pressure draw on the system, but also increasing the efficiency by a lot, and not necessarily the cost associated with it, because half of the job was like already to replace that coil in the system. So combining and leveraging those savings is one of the key examples we proposed. Another example was the conversion of the existing steam boiler from steam to hot water. What you see on the screen right now are nozzles that were welded in the bottom drum of one of the steam boiler in the central heat plant. So basically, we came up with that solution not to replace those, yes, old boiler, but still usable boiler. They were like built to to be used for many years. So having this solution instead of replacing, it reduced time for implementation, because we don't have to demo those big boiler and come up with a new boiler, find space and have a very complex schedule to replace all those boilers, because we are reusing most of the existing asset in the central heat plant. It's just that engineering had to be done in a way that it's going to work for future. So we spend more time, yes, in engineering, having specialists look at those boilers on how we can convert them to hot water, but it paid off at the end. The third example I have on the screen is I spoke earlier about the process load we had at Brown University. So we have this high pressure steam system. There's no real efficient way of transforming. Like, you're not going to install a gas unit because you want to get rid of steam. You'd better to just find a better way on producing steam. So what we've did is we've installed those high pressure steam boiler, but we've also engineered a system so we can recover heat from the stack. So basically, we've got those 4 high pressure steam boilers that are operating right now at the efficiency of a hot water boiler. So we were able to connect these heat recovery system into our hot water loop, basically increasing the whole campus efficiency at the same time. So that's what it meant really for us investing in engineering.
Then we also had out on campus a lot of these steam hubs that ecosystem addressed, and this diagram here actually shows our RISTON quad, which is 9 dorm buildings, the sort of light blue ones in the middle, Sharp Refectory, which is our largest dining hall, and then a small library and our infirmary in the lower left. And all of these were fed. The distribution of heat in this complex was by steam. So the high temperature hot water made steam, and it moved around all these. You can see the green lines, those were the steam distribution lines. This is not a small complex. I mean, it might be to some people, but 11 buildings, 9 of which are dorms, over 1,000 beds, and nearly 500,000 square feet. Okay, and we needed ecosystem to find an innovative way to save energy in here, but also to simplify everything. So Frederick, how did you guys do that anyway?
That's a very good question. So we said investing in survey earlier, and the first thing we saw, let me just come back on that slide here, is Brown had this steam distribution system all located in tunnels all around the quad, and surveying those systems, we saw that there was 2 steam supply piping. One of these were an old process steam distribution piping, smaller than the existing one that distributed low pressure steam. So we had this idea of reusing those 2 pipe to create an inverted return. So not spending the time in those tunnels looking at how we would have converted, we would never find this solution that basically unlock the quad conversion, because having a bigger pipe in a smaller pipe, it's possible to arrange the loop in such a way that you're creating an inverted return. So basically, most of the flow is supply on one side, and your return pipe is smaller for the first portion of the loop. Then, if you swap those two pipes in the middle of the loop, then you're having your return piping bigger and your supply piping smaller. So that's what it looks schematically, and on the quad, it looks some things like this. But we still had to do some more modification, but they were like very small compared to installing piping all over the existing dorm, because anyway the ceiling were all crowded with different type of pipe, and you also had like the high temperature hot water supply that was passing in half of the building. So that unlock our ability to transfer from steam distribution to hot water distribution in only one summer. So as David mentioned, yes, we have to remove all these heat exchanger to replace it by a valve, but we didn't have to install like feet and feet of piping, just those two little section on the start of the loop and in the end of the loop, so we could have completed our inverted return.
Brown really saw the innovative nature of this, and 3 years later, everything's working great, by the way. But we still wanted to mitigate the risks, and so we did seek out and find ways to avert any risks that we perceived from reusing this equipment. And as Frederick said, that those process steam lines, they'd been out of use for 40 or 50 years. So I think everybody was wondering, is there some kind of special student thing that's being used or something? We weren't sure. Anyway, risk mitigation was very important to us. And this is how the project set things up. First of all, planning. In the planning process, it was very important for us to find the right resources, including professionals that know the equipment, even if the equipment's really old. And that sample about the converting the boilers in the heat plant using the nozzles and everything, we had some great expertise here in New England, and also some expertise from up in Canada that kind of collaborated on getting that solution together. Funding. We set up a contingency fund because we recognized that we were going to be doing testing on all these lines that we're going to reuse, but there might be someone in the process that says, look, I know this test that passed all the tests and everything, but I still want these pipes replaced in this one case. So we set up a contingency fund for that. That contingency fund was a small fraction of what it would have cost us to put all new piping in. And at the end of the project, we ended up using a very, very small portion of even that contingency. So the cost reduction on piping was huge. And I think everybody felt better that they had that contingency fund, that if they felt like they really wanted to replace something, they could. Facility condition index. We had a lot of old gear, like in the hubs that we just talked about in RISTON Quad. There were a lot of old steam converters, condensate pumps, and everything in there. The winter prior to us converting, we actually had one of those steam converters spring a leak on the bottom. We had to get in there, and probably the coldest day of the year, and have somebody weld a new bottom on it. So we actually eliminated a lot of old gear. So our facility conditions index got much better. So physical testing, we set up a testing protocol for anything that we were going to reuse. We did some non-destructive testing, and also some destructive testing where we'd cut out sections of pipe and check for wear and tear and such. And if the pipe passed that, then we could reuse it. If it failed, the project took care of replacing it. And actually, Ecosystem had predicted which pipes they would need to replace, and pretty much they were spot on. So, and that was already in the project costs. Terminal equipment, we wanted to test all those air handlers where we changed out seam coils with a face and bypass over to some kind of glycol coils. We took some preliminary balancing to see where we were as far as the pressure drop, took a look at the pressure drop expected for the new coils, and made sure that the fans had the capacity. And pretty much in all cases, I think, because they were mostly face and bypass, we actually decreased the pressure drop across the coils in these air handlers. And then finally, commissioning. And commissioning for us started way back even in the planning process. We included an engineering firm to do a peer review on all things. So when we had a 30% design review, a 60% design review, et cetera, that peer review engineer sat in, made comments, and we addressed concerns from that. That made everybody feel better. But also at the end, we made sure that we did proper, functional test list, checklist, and everything, got all that done to make sure that when that first cold day of the fall came up and we started the heat, everything was going to start properly. Next slide. So what was the result? All that innovative planning, engineering, all that risk mitigation that we took, we really maximized outcomes. Brown would not have been able to do this project without using existing assets. The boilers at the heat plant, reusing piping, repurposing air handlers, things like that. There's no way we could have done this project without it, first of all. Reduce disruption in facilities. We had a lot of work done in occupied dorms and in occupied, laboratory spaces, okay? By being able to reutilize equipment, there were, very, very few disruptions, if any. That dorm complex that we just talked about, those dorms are occupied year round. Maybe 3 weeks in June, they're very lightly occupied, but then summer programs come in. So instead of running, putting new pipe hangers in throughout the complex, you've got impact drivers going, 12 hours a day. We didn't have that. We repurposed, the stuff was already there, it was installed, insulated. So it actually saved us a lot too on security details and things like that. So much less disruption. Easier change management. A lot of the gear that at the end of the project was gear that the guys had seen before. So they didn't have to, relearn everything. Accelerated project timeline. There is no way we would have got this project done. We got the total project done in 3 years. It would have taken us at least 10 if we'd followed our normal procedures and not reused some existing assets. And then finally, and most people won't think about this, but there's a sustainability aspect to reusing your existing assets because there's embedded carbon. If we had to rip out those 3 80,000-pound steam boilers and throw them away and then produce new ones, there's a carbon cost to that. Same thing with all the piping and the insulation and everything. So don't forget about embedded carbon and the advantages of repurposing the gear. And then over to the right here, this little thing in red, the risks of doing nothing, and they are always higher than the perceived risks of moving forward. We had a lot of old gear that we got rid of. All that deferred maintenance is gone. We don't have to worry about all those steam converters failing on us in the middle of the winter. So yes, there are risks to repurposing, but you can follow the right mitigation. You can set up mitigation protocols so that you don't have to worry about it as much and everybody's much more comfortable about it. Next slide.
So today's takeaway are, please make sure you consider existing asset value when you do asset renewal project. Put your investment into engineering because that's where you're gonna see the value of not disposing on everything on campus or any of your system. Those are service purposes, and when you tear everything out, you have to go out of your normal way of operating. So if disruption are critical, then focus on those assets because those are the key elements for you to do those projects without having a very, very big budget to just like do the same exact purpose as before. So having a holistic understanding of your entire system is the key. So make sure you got the right people with the right knowledge beside you, and it's always external and internal because all those people internally at Brown University gave us all the information we needed to find the solution they were looking for. So this team effort paid off for us in Brown during that project. So those were the takeaways from today's presentation. I hope you enjoyed. Here's our contact information. Feel free to reach to us. Thank you for listening.
Yep. Feel free to reach out. We'd be happy to answer any questions you have. Take care.